All right, higher order derivatives. This is 3.5. Higher order derivatives is when we take more than the first derivative. So we'll start with y equals sine x and y equals cosine x. When we take the derivative of those, we get dy dx equals cosine x when we start with sine x, or dy dx equals negative sine x when we start with cosine x. And I'm going to do the first four derivatives. And when we do that, we see that by the fourth derivative, for both of them, we're back where we started, which is really neat. For sine and cosine, y is the same thing as the fourth derivative of y, which means every four derivatives cancel out. So like the eighth derivative should be the same. And it should be the same as the 12th derivative. Every four, we're back to where we started. And we keep going. So every fourth derivative for sine and cosine is the original function. I don't know about you, I think that's pretty cool. It's actually super important, as we'll see in a second. We want to find the 33rd derivative of y with respect to x if y equals sine x. So try to figure that out, knowing that we're going to do this pattern that every four is back to the original. All right. So what I did is I did found how many times 4 goes into 33. It goes in 8 times. So 4 times 8 is 32, and I need one more to get to 33. So the 32nd derivative will be sine x, right back to where we started. It's a multiple of 4. And then I took the derivative one more time. And the derivative of sine x is cosine x. Okay. Here's one for you to try. Find the 55th derivative of cosine x. All right, I will assume you did that. Give it a try. 4 goes into 55 13 times. 4 times 13 is 52, and so I need 3 more. So I went all the way up to the 52nd derivative. That gets me right back to where I started with cosine x. And then I took the derivative one at a time. So the first derivative will be negative sine x. Next derivative is negative cosine x. And our third derivative will be sine x. So the 55th derivative of cosine x is sine x. Okay? And this is very important. It leads to one of the most important equations in all of science. It's called the wave equation. The wave equation is based on this. The wave equation describes a one-dimensional wave's displacement u over time t and position x. So like we have it could be something like this, and then like a guitar string, and you pluck the guitar string, and it ends up creating waves. And depending on how you pluck it, might create different amplitudes and different frequencies. So there's different ways it can happen. And we're not doing this yet. This curly D is actually partial derivative. You'll learn that in Calc 3. I just wanted to show that this is related. And it's really important, this trig thing. But it requires the second derivative with respect to time to be the same thing as the second derivative with respect to x times c squared, where c is the wave speed. And like I said, this little curly d is a partial derivative. We do that in Calc 3. And that makes this what is called a partial differential equation, a PDE. But equations in the form sine of x minus ct, sine of x plus ct, cosine of x minus ct, and cosine of x plus ct all solve this equation. And you'll learn this about this in physics when you go into physics. In Calc 3 or higher classes, we will actually look at a three-dimensional wave, not just along a string, but maybe a wave in the ocean or something like that. Lots of things travel as waves: light, sound, earthquakes, water. A lot of things are affected by waves. So like this is a really important equation. And since the second derivatives with time and space have to equal each other, that occurs with trig functions, sine and cosine in particular. Okay. Next, we'll do another example. A particle is moving along a coordinate axis in such a way that its position at time t is given by s of t equals 7 minus cosine t. We want to find the velocity and acceleration when time equals 3 pi over 4. And then compare these values and decide if the particle is speeding up or slowing down. So you want to take the derivative and then plug the values in and see what you get. We've done problems similar to this that did not have trig functions. So you know how to do this, just the trig function part is new. I will assume you pause the video and give it a try. The first derivative will give us velocity, and that would be, if we take the derivative of 7 minus cosine t, the derivative of 7 goes away. The derivative of cosine t is negative sine t, but it was already negative, so two negatives make it positive, and we get positive sine t here. And if we take the derivative again, we get acceleration, we get cosine t. So I plugged in 3 pi over 4 into both of them. We get sine of 3 pi over 4 and cosine of 3 pi over 4. They're both square root of 2 over 2, but the cosine one is negative. This is in quadrant 2 over here, right there. And that's negative root 2 over 2, comma, root 2 over 2 on the unit circle. So velocity is positive, so the velocity is to the right, it's positive. But acceleration is negative, so the acceleration is backwards, which means we're hitting the brakes. The particle is actually slowing down. If we're going a certain speed in one way, but our acceleration is in the opposite direction, we're slowing down. If the acceleration is in the same direction as velocity, we're speeding up. Here's an example of something that isn't a particle, but actually something that happens. A block is attached to a spring moving vertically. We did it vertically so that like there's no friction with the ground. It's attached to a spring moving vertically. Its position at time t is given by the equation s of t equals 4 sine t. It does actually follow a trigonometric function because as it gets near the end of its stretches, it slows down and it goes back the other direction. And it keeps going back and forth. So like a spring at rest, if you pull it down, it's going to get down to the bottom, but then it's going to shoot back up to the top and go past and go all the way up. And it's going to come back down. And so if you model the up and down, it's doing this. It's making a wave. So that's the idea here. We take the derivative twice to find the velocity and acceleration functions. The derivative for velocity would be 4 cosine t. The derivative of velocity will give us acceleration. That's negative 4 sine t. And we're going to do it at 11 pi over 6. So if we plug in 11 pi over 6, we are over here in quadrant 4. This gives us a reference angle of pi over 6, or 30 degrees. The main angle is 11 pi over 6, or 330. And so cosine of 11 pi over 6 is square root of 3 over 2. If I multiply that by 4, I get 2 root 3. Sine of 11 pi over 6, this is below the x-axis, and sine is negative down here. So sine of 11 pi over 6 is like the sine of pi over 6, but negative. So that's -1/2, and we're multiplying it by -4, we get a 2. The velocity and acceleration are both positive, which means they're both going in the same direction. The block is actually speeding up at this point. So it's probably up here and compressed like this. And the compression is, and it's already started to go downwards, but the compression, it's trying to decompress and it's forcing it to go faster that way. After it gets past the equilibrium point and it goes this way, the acceleration starts to be in the other direction. That's a little bit of physics for you. This is also a physics topic. Okay. And that's it for these videos. Peace.